ninth grade kids at home, the YouTube video of me forgetting the quadratic equation will get a kick out of it. But okay, so lambda is equal to 2 cosine theta plus or minus the square root of b squared, which is 4 cosine squared theta minus 4 times this times this, all over 2. Okay, so this is, so we can factor the 2 out and the 4. The 4 coming out of the square root gives us a 2. So there's a 2 here, and then we're dividing by 2, so that 2 goes away and this 2 goes away. Cosine squared of theta minus 1 is equal to negative sine squared theta. That can be written, so this can be written as cosine theta plus or minus. We can take the negative outside of the square root, that's an I, and the square root of sine squared of theta is sine theta. So this is e to the plus or minus I theta. Okay? So so we have 3 eigenvalues for a rotation matrix in 3-dimensional space. There are 3 eigenvalues. The eigenvalue 1, the number 1, and e to the I theta and e to the negative I theta, where theta is not just some angle, it's the angle of rotation. Okay? This is the same theta as in the axis angle formula, theta. So if I give you a rotation by an angle theta around any axis in space, the eigenvalues of that rotation matrix are going to be 1, and then e to the I theta and e to the negative I theta. Okay? Any questions about any of that? It's sort of hard for me to judge whether I'm going too far beyond, or just it's late in the afternoon, or, well, I'll just keep talking. If there are no heckling, no, you know, it's always a balance, right? Between, on the one hand, people falling asleep, and on the other hand, people getting lost and then falling asleep. But I'll do my best. Okay, so those are the eigenvalues of a rotation matrix. And I'll talk about one other, and this is all related, okay, to the ultimate goal of understanding rotations and how to reorient satellites. There's one other parameterization that I'll talk about, which is the Cayley parameters. And so this is, so we just finished, page 114 in the note that I handed out. Now we're doing 115 and 116, 115 through 117. Okay, so we've already seen that there's one relationship between rotation matrices and skew-symmetric matrices. Namely, if I take a skew-symmetric matrix and I do the matrix exponential, I exponentiate it, then I get a rotation matrix. Okay? Skew-symmetric matrix becomes a rotation matrix if you exponentiate. There's another relationship between skew-symmetric matrices and rotation matrices, and it works like this. Suppose I give you, so here we have a coordinate system. I give you a vector little x, and then I rotate it. So, well, I'll keep with the notation in the book. So I call this a vector capital X, and I say I take capital X and I apply a rotation to it, and I'll call the result little x. So this was capital X, and then I rotate and I get little x. So this is a notation that they use in continuum mechanics, where you start out with a referential set of coordinates, and then you deform, and then you have new material coordinates, little x, that result from the deformation. So if I look in the plane, so if these two vectors are in a plane, any two vectors define a plane, right? If I look from the normal direction to this plane, I see two vectors that have the same length, because a rotation doesn't change the length of the vectors. And Cayley did a little construction. He said, well, suppose we make a parallelogram. Actually, it's more than a parallelogram, it's a rhombus. These four lengths are all the same. Okay? So again, if I look in the plane normal to these, the direction normal to this plane that's defined by these two vectors, I'm just going to see a rhombus. Okay? Now, going back, a few thousand years, fortunately this problem was already solved by the ancient Greeks, which is if you have a rhombus, then this chord and this chord intersect each other at a right angle. So that won't be true for a general parallelogram, but it will be true for a rhombus. Or maybe it's true for, I'm not sure if it's true for a parallelogram, but it is certainly true for a rhombus. And so we can do a little geometric construction here. So if we take little x plus capital X, which seems like a strange thing to do, except that it's going to result in this Cayley parameterization of rotations. We take little x plus capital X. By definition, little x is equal to r times capital X. So this is equal r plus the identity times capital X. Okay? And if we take little x minus capital X, then that's going to be equal to r minus the identity times capital X. Okay? So far, so good. Now, the thing is that little x plus capital X, that actually defines this vector right here. And little x minus capital X defines this vector right here. So if you believe the ancient Greeks, then little x, what we have here, plus capital X, dot product with little x minus capital X should be equal to 0, because these two are perpendicular to each other. Okay? So we can, using this side over here, we can write that as capital X transpose times r plus the identity transpose times r minus the identity times x should be equal to 0. Okay? Now, okay, so that's true, but that's not what I wanted to do. So instead, what I'm going to do is say, let's invert this expression right here. So, and this is where the eigenvalues come in handy. Okay? We just talked about the eigenvalues of a rotation matrix. Lambda 1 of r was equal to 1, lambda 2 of r. It doesn't matter what we call 1, 2, and 3, but there are 3 of them. is equal to e to the positive I theta, and the other one is equal to e to the negative I theta. Okay? So now there's an interesting fact about the eigenvalues of matrices. If I know the eigenvalue of a matrix, if I know the eigenvalues of the matrix A, and then I add to that a constant times the identity matrix, then the eigenvalues of this are equal to the eigenvalues of A plus C. And you say, well, wait a minute, that's pretty tricky because where's the, you didn't do any characteristic polynomial or anything, but you actually don't need to do that because if you look at the definition of eigenvalue, an eigenvector, A times V is equal to lambda V. So if I ask what is the eigenvalue corresponding to this, A plus C times the identity times V is equal to AV plus CV. And so if I've already solved this one over here, then, so if I call this, let's say, lambda prime times V, so lambda prime being the eigenvalue corresponding to this sum, then what I see right away is that AV is equal to lambda prime minus C times V. But I know that A times V is equal to lambda, so this has to be equal to lambda times V. So this means that lambda prime minus lambda prime minus C has to be equal to lambda, which means that lambda prime is equal to lambda plus C. So, in other words, the eigenvalue of A plus C times the identity is equal to the eigenvalue of A plus C. So, if you take a matrix and you add to that a constant times the identity, what you do is you shift all of the eigenvalues by that constant. Okay? Okay, so why am I talking about that? Well, here we have an R plus the identity. I know what the eigenvalues of R are. They're all these three. So the eigenvalues of R plus the identity will just shift all of these by the number 1. So the one eigenvalue of this is going to be 2. Another eigenvalue of this is going to be 1 plus this. And the third eigenvalue is going to be 1 plus this. And the reason why that's important is because if theta is not pi, theta can be anything else in the range 0 to 2 pi, but as long as it's not pi, then all of these are going to be non-zero numbers. If theta is equal to pi, then these are going to give me -1. And when I take -1 and add it to 1, I'm going to get 0. So, and if I have eigenvalues that are 0, then I can't invert the matrix. And so what I want to do here is invert this matrix. In other words, I want to isolate X over here. And so what we do, using this fact that whenever theta is not equal to pi, we can actually invert this matrix. So if this holds, then we can write capital X is equal to R plus I inverse times little x plus capital X. Okay? And we'll handle the case when theta equals pi as a special case later, but for all the other cases, every possible rotation angle from 0 to 2 pi, or if you prefer from -pi to pi, we can do this this inversion. Okay? Now, then what we can do is we can take this result and feed it back in over here. So we get x minus capital X, which is the left-hand side here, is equal to r minus the identity times r plus the identity inverse times x plus capital X. Now, I could not have done this with r minus I. r minus I is not invertible. And the reason why it is not invertible is because this is just like this a plus ci thing that I just talked about. Here, if c is equal to -1, -1 is multiplying I, the eigenvalues of this are going to be these shifted by -1. And if you take the number 1 and you subtract 1, you get 0. So this will never be invertible. This is always a singular matrix. You can't invert it. You can invert this one all the time except when theta is equal to pi, and you can never invert this one, which is okay because we don't, for what I'm doing here, we don't have to invert that one. So we have this expression right here, and now we're going to use this fact that I mentioned over here. We're going to take the dot product of this and this, which is the same as pre-multiplying this by little x plus capital X dot product with this, which is the same as the transpose, is we'll put in a little x plus capital X transpose in here. Okay? And that has to be equal to 0 because of that perpendicularity of the two bisectors over there. Okay? Now, so the whole reason for this construction is because it says something about R. Okay? And so let's rename things. Little x plus capital X, we could call that Y. So this is Y. And so, and this matrix right here, I'm going to call that S. So what we have is the equation Y transpose S, Y is equal to 0. And the capital X that we started with was arbitrary. And so the Y that we get over here is also going to be arbitrary. In other words, we can ask the question, if Y is arbitrary, what does that say about S? Any guesses? Other guesses? So 0 is a common guess, and if I gave you A transpose S B equals 0 for arbitrary A and B, then S equals 0 would be correct. But a tricky fact, in fact I had to correct a professor about this on a GBO one time. He was asking a graduate student a question, and the professor thought that S was equal to 0 because of this, but actually it's not. If you think about it, there is a way for this to be equal to 0 when S is not 0, for this case. For this case, if A and B are both arbitrary, S has to be equal to 0. But that's not what we're looking at. We're looking at the same vector on both sides. Okay? Well, if S was the same as the vector S cross Y, then S cross Y would be perpendicular to Y, and Y dot product of this would have to be equal to 0. So in other words, if S is skew symmetric, then that will be equal to 0. Okay? And it turns out that that's the most general case. When S is skew symmetric, then this will be 0. So what that says is that r minus the identity times r plus the identity inverse has to be equal to a skew-symmetric matrix, which is kind of interesting. So what we can then do is we can try to reverse this equation. Instead of getting s in terms of r, let's get r in terms of s. Okay? So if we want to write r in terms of s, now we're going to multiply on the right by r plus the identity. So we have r minus I is equal to s times r plus I, right? Which is, this is the same as sr plus s. Now I'm going to bring this over to the other side of the equation. So we have r minus sr is equal to I plus s. And then we have I minus s times r is equal to I plus s. So then the question becomes, can we invert this matrix? Can we invert this matrix to find r? Remember, S is a skew-symmetric matrix. Now it turns out that the answer is yes. And so we'll do one more eigenvalue kind of calculation to prove, because if all of the eigenvalues are non-zero, then you can invert the matrix. So we're going to use basically the same proof we did for the symmetric matrices to talk about the eigenvalues of a skew-symmetric matrix. So if S is equal to negative S transpose, and I tell you that S times V is equal to lambda V, so here we're talking about eigenvalues of a skew-symmetric matrix. So we'll do the same thing that we've done before. So we do SV equals lambda V. We take the complex conjugate, and it's real, so it's the same. And then we take the dot product, and, well, let me see if there might be a little subtlety here, just to check. And okay, so what's in the book is a different way. Actually, I calculated the characteristic polynomial on page 115. So that's one way. Let's see if this way goes quickly. If not, then we'll just do the characteristic polynomial. If we take the dot product of this with itself, we may want to multiply this by V transpose and this by V complex conjugate transpose. And then we get this. And here it's skew symmetric. So what we get is that if we take, remember this is a scalar now. So that if we take the transpose of the scalar, we get the same thing back. And so then this is, when we do the transpose, we get a V complex conjugate transpose S transpose V, but S transpose is equal to negative S because it's skew symmetric. So this is equal to the negative of this, or put another way, this is equal to negative this is equal to negative this. So if we equate these, what we get is that lambda v dot v conjugate is equal to negative lambda conjugate v conjugate dot v. As usual, this cancels because it's not zero, so we get that lambda is equal to the negative of its own conjugate. And what that means is that lambda is equal to an imaginary number times something. Okay, so in other words, it's pretty much the same proof that we did for the eigenvalues of a symmetric matrix. For the eigenvalues of a symmetric matrix, there was no negative sign here, and we got that lambda was equal to lambda complex conjugate, which meant that lambda was real. Here, we have exactly the opposite. So lambda is equal to negative lambda conjugate, which means that lambda is pure imaginary. Okay. Well, if lambda is pure imaginary, then if you shift it by the number 1, it's still going to be a complex number that's not 0. So in other words, this matrix will still be invertible. Okay? So the fact that the eigenvalues of a skew-symmetric matrix are pure imaginary means that by adding or subtracting an identity matrix from them cannot make them 0. You can't take a pure imaginary number and shift it by a real number to make it 0. So that's sort of a maybe too much detail for this hour in the afternoon, but what it means is that we can invert this matrix. And if we invert this matrix, what we get is that R is equal to, and we're inverting it on the left side, so it's I minus S inverse times I plus S. And this is Cayley's formula for rotation, which says that so before we're talking about exponentiating a rotation or a skew-symmetric matrix, this says that if I give you a skew-symmetric matrix S, it can be any skew-symmetric matrix S, and then I take I plus S and I multiply it by the inverse of I minus S. That would be a rotation matrix, which is kind of surprising, at least to me, that you can just take this skew-symmetric matrix and do this and you will be guaranteed to get a rotation matrix. And and remember that a skew-symmetric matrix has 3 independent pieces of information in it. It has S1, S2, S3 that sit inside of that 3 by 3 skew-symmetric matrix. And that these are 3 parameters that can be used to describe rotations. Okay? So in general, rotations in 3-dimensional space, there are 3 parameters. You could do, the alpha, beta, gamma for the Euler angles. You could use the x1, x2, x3 for the exponential parameters. You could use theta and the n vector in the theta n parameterization, theta n. Because n is a unit vector, you could describe it using polar or spherical coordinates, right? Cosine theta, sine theta, cosine phi, sine phi. So even though n is a vector with 3 components, it only has 2 degrees of freedom. So 2 degrees of freedom there. Well, I shouldn't call this theta. There's this theta, which is the angle of rotation, and then there are these angles that describe the vector, unit vector n, which is the axis of rotation. Okay, so the point is that there are all these different ways to describe rotations. They all have 3 parameters, and this is another, okay, another 3 parameters. And some people like this Cayley parameterization. For instance, Professor Kubilarov has done a lot of work that uses this Cayley parameterization. And on page 117 is the explicit form for what the rotation matrix using these Cayley parameters looks like. And these are all interchangeable in the sense that if I give you a rotation matrix described using Cayley, then you can calculate what the corresponding axis angle parameters are, or the corresponding Euler angles are, just like we went from ZXZ Euler angles to ZYZ Euler angles. All of these different parameterizations are interchangeable. Okay, and we talked about this somewhat previously. Actually, we did it for Euler angles, but I want to generalize the discussion to angular velocity. So, so we had this expression for what the body-fixed and the space-fixed angular velocity of a rigid body looked like in terms of Euler angles and rates of Euler angles, right? And so we can generalize that discussion to the case where we have any of these different parameterizations, and that's important because in that microsatellite reorientation problem, we had a parameterization which was not Euler angles. It wasn't any of these. It was R of, let's say, I'll use alpha, beta, gamma, but it's not Euler angles. You had a rotation, say, by R of alpha, then R2 of beta times R3 of gamma, and then the flippers reversed, but in reverse order. So R3 of minus alpha, R2 of negative beta, actually I guess it was R1 of negative gamma. And so we get this parameterization of sort of based on the flippers, how much they rotate. And the question was, we start out at some orientation, which without loss of generality, we can take that as the identity matrix. So that's where our world frame is pinned, where the satellite is originally. And we want it to rotate in some way, to some desired relative rotation from where it starts to where it ends. So the question is, how do we figure out what the alpha, beta, gamma need to be in order for, in one sequence of flips, for the satellite to rotate? And if we can't achieve that because of limitations on how much the flippers can move, then we could do it in steps. But we want those steps to be going in the right direction. Okay? So if we do some flipper movements, we want the rotation to change in the right way so that it's moving in the direction of where we want it to go. And so the procedure in the paper involves Jacobian iterations. And so what I want to talk about now is what do we mean by a Jacobian in the context of rotations and in the context of a rotation parameterization. So I'm going to say R is parameterized by some Q. So three numbers, Q1, Q2, Q3. So the discussion here is a generalization of what we talked about quite a while ago with Euler angles. But here Q could be any parameterization of rotations. It could be Euler angles, it could be the Cayley parameters over there, it could be theta, lambda, phi, the angles in the axis angle parameterization with n being described as angles. It could be x1, x2, x3, this matrix exponential parameterization that I just described. It could be, or it could be this alpha, beta, gamma, with the angles in the microsatellite with flipper parameterization, for lack of a better name. So if I give you R of Q, the question is, in any of these parameterizations, and Q is a function of time, then we're talking about describing rotations that vary with time. And so then we can ask, what are the body fixed and the space fixed descriptions of angular velocity for a given parameterization R of Q? And so it pretty much goes like what we talked about in the context of Euler angles. We know that the body fixed description of angular velocity is going to be the vector R transpose R dot, and the space fixed version of angular velocity is going to be the vector. Here's another way skew-symmetric matrices show up, right? So we've been talking about skew-symmetric matrices over there, but this is a skew-symmetric matrix that shows up when we take derivatives, and we've discussed this previously in the class. And